As of now, it's clear, right? So I think, if recording doesn't happen. So the task, what actually was given to me, it's quite clear. I think we had a clearer understanding of how blinking different LEDs and all. We have an RGB LEDs, we have normal LEDs. RGB LEDs we haven't done, but initially within due course of action, of course, we'll get it done. But the most important thing is that two things happen parallelly, simultaneously. One, taking the value from the computer keyboard. Secondly, doing something connected with the Arduino board parallelly, right? And one cannot alter another, one cannot slow down another. That is the I think the beauty of the code. So I mean, code, it's quite straightforward. I just want to make you sure that this is as similar as the previous code you have seen in case of like GRYB, right? We type a key from the keyboard. Let's R for red, G for green, Y for blue. Okay. And white for W for white, and it will blink that particular corresponding LED for a number of times, for 7, 8 times or whatever. Similarly, I just I think it's better to put a copy of the basic things, and then so that I think it's no need to write all such things. I make copy of these things so that we may concentrate on the logic, right? I think we don't need all the other codes, I think. No, we don't need that. So that is for sure. We have, now we have 5 LEDs, red, green, yellow, blue, and a white LED is also there. So now within serial printle, I'm just writing this code in a different manner, just to make 2 things happen parallelly. Okay, just watch me carefully. So if we know, Ravi, that if serial available, right? So serial, sorry. He is prominent here. If serial dot available, it means that press something. Serial dot available greater than 0 or equals to nothing. It means that serial dot available is 1. That means at least 1 character is available from your keyboard to the serial buffer and not. Okay. So
what if without writing anything, we press the enter button?
It will take a simple space. I mean, what if once, for example, that you don't write any character, so it takes a space, and we have a consideration. We have a check whether the character is empty. The character or the string is empty. It will do nothing unless and until the string is non-empty. When the string is non-empty or the character read from the keyboard is non-empty, then only it can perform certain tasks. Okay. Yeah. The similar checking needs to be done over here. I think that's a good question. So we'll perform that checking as well, whether the string or the character is empty or not. Fine. So anyway, character, let's assume this is let's type something equals to serial.read. Fine. Okay, so then we type something serial.println the received receive character is, or receive input is, receive input is so string type. Fine. So we have another character variable ch. So ch equals to, I can put just to make sure to save the variable another character so that this variable remains unchanged, and then we just open and close the loop. Okay, we don't need to do anything. Now I write a function. For example, name is, let's say, blink. Okay, blink is a function. It's not your library defined blink. Blink is a user defined function. We need to write the blink. Okay, so blink. Fine. Now void blink. So first we cross check if this ch not equals to yeah, that means empty. Okay. I mean, if it's a string, it will be like this one. It will be like this one is basically empty, but it's a simple character. So we can put a two single quote separated by a space, right? So if ch not equals to space, that means character field ch is not non-empty, then it can perform certain tasks. So we have if ch equals to small r and ch equals to caps r. I think it's better to put smaller, right, Ravi? I think you know the basic logic. Okay, fine. Just by putting an or sign, you can add when ch equal to smaller or ch equals to so. Yeah, so that is sufficient. Huh. So if ch equals to r, so we put simply digital, right? Yeah, r means red, so red is basically high. Delay, let's say 100. Okay. That one if condition is now else just copy equals to let's say g green. Okay, fine. Next we have yellow. We have blue. We have white. Okay. This is the final if conditions and this. Yeah, right. I think the board is connected to. Yeah. Okay.
If and else it can come like it's not in a sequential way, right?
Sorry.
Okay. No, like first we wrote if, after that else if. The next again it
else
is
it means
coming as a if.
oh sorry. Oh shit. Okay, I'm becoming blind. So sure. Else it means at a time it can check one. If you press a, if obviously the same thing happens, but every time, let's say if I keep on pressing everything if what means that if this condition is true after satisfying I mean getting the things not written inside this open and curly braces closing, it comes over here, it comes down to here, it will again cross check. Although the statement is false, but still it will unnecessarily waste processor to check condition for the rest of the cases, which are not true actually. So it's better to put them in a else if model. Okay, so
No, I didn't get it. So if you are writing if.
okay, nice. See, if we write all if condition, what happens? For example, if c is equals to or something, if c is equals to c something, all are if.
Yeah.
But at a time, one condition can be true, other remain as a false, right? That is true.
Yeah,
but
yeah.
as we have written all our ifs, the processor does not know which is true, which is false. Even if it comes to let's say first if and if it is true, but as you have written everything on the if, still after performing the tasks or statements written inside this open and closing curly braces of the first if, it comes down to the second, third, fourth if, and every time it checks whether the condition is true or not. But once you put else if, after satisfying one condition, it does not bother to look at the other condition. It doesn't have to bother to other conditions, right? Because others happen to be true. So anyway,
So if you are writing multiple else ifs, then the case is not same like if.
Definitely, case is not the same. So anyway, so let me open my camera. Where is Idion? Right. So just Gideon. For Gideon. I think which is a better view. Yeah, that is the better view, right? That is a better view. Okay. Yeah, first, I think this one, I think it was.
No, it's fine. It's fine. I can see.
So it's R, right? First I'm writing R, right?
Yeah.
Still, it keeps blinking. Again, I'm pressing G. Without having any delay, without getting a bit delayed, it straight away jumps over here because I've just taken the function out of the main loop. I've written in a separate functions, and I keep calling the function as many times as requires. If you see W, white.
So unless we press the next one, this keeps
Next button, this keeps and this LED keeps blinking indefinitely. Okay. This is the task actually, but this is these two things actually are happening parallelly. You might understand it a little bit later when we are into the actual IoT and other field, but probably in your I mean other projects also, that we need to perform several tasks at the same time. But you need to distinguish which task is to be given the highest priority or the highest preference, and which task is to be given, for example, modest priority or the modest preference. Actually, this is how things actually, I mean, everything's set apart. Anyway, it's a small task, but it's a good one. So let me just put my camera on. I just copy the program to you. It might stay with you just to clear a few of the basics that you have studied. Yeah. Please maintain a proper Google Drive, okay, for you and me also, because I'm kind of messed up person.
I missed to make this one. Yeah.
Okay,
Sure. I'll start this week maybe.
Yeah, sure. Acha, like I think for me it's a kind of
just 2 minutes break.
Yeah, sure. I think 2 minutes break. Can we take a 5 minutes break after once we are
done? I mean to say, yeah, I have 5 minutes.
Once the discussion will be over, then we'll take a 5 minutes. Anyway, I think for me, it happens to be the utter stupidity to make you understand what the rotary encoder is all about. But you know everything. What I'm going to do, or what I've actually purchased the rotary encoder. Okay, I think today it reached out to my address, and just because of some of the projects lingering on my head, so better I thought that better I should start from the very basics concept of rotary encoder. I know that it will know. I mean, most of the people actually know. But now tell me, Ravi, one thing in a quick nutshell. What is the purpose of rotary encoder? Why do you use the rotary encoder? Whether it's a sensor or it's an actuator. I mean, if you are assigned to distinguish between, distinguish rotary encoder as a sensor or an actuator, which category it should belong to?
It's like an actuator. I mean, simple. It's not like a sensor.
Yeah, it's sometimes you can see it's a, but at the same time it is. Microcontroller is basically taking or inputting reading from the 2 points, right? The clock and the DT. So in that way it is sensor, but at the same time it is providing some of the mechanism internally, which is the actuator, right? So rotary encoder is a you can say it's a shaft encoder also, which converts its angular rotational or the angular displacement into an analog or a digital voltage. Right now we are dealing with the all digital voltages. So we have a slotted disk actually connected to this pin ground. We have a VCC ground, and we have a switch. I think this Irian is there. So
yeah, it has a switch also. When we push it,
right. So this is basically the rotary encoder of mine, which actually delivered to me. Yeah. So this is a switch. Okay, this is the clock. This is DT. Okay.
Now that's
Camera.
it's negative. Ground.
Sorry.
No, ground VCC. Clock.
Switch, clock,
Switch.
and negative clock. What you can say DT, and the rest of the switch. Okay.
Yeah.
Because you have this switch and you have clock, right?
Yeah.
Okay. One second. Camera. iPhone camera is not working. Yeah. As of now, it's clear. Clock DT switch plus minus up. So sometimes clock or DT the point is whatever different anyway. So so what happens in our cases basically that it's a slotted disk connected between the this ground pin C, and there are 2 pins 1 and 0. So when you turn the knob, the moment actually you turn the knob for the radio and the other graphic equalizer, so this AB actually A and B that provides a contact, or that establishes a contact with the common ground C in a such a order the way actually you are turning the knob, whether you are turning the knob in a clockwise direction or anti-clockwise direction. So these 2 pins, I mean maybe the electronics guy is quite simple, and for you also it's quite simple because we have gone through the motor, DC motor and AC motor also. We know how phase shift occurs, right? So when the signals are 90 degrees out of phase shift, they will occur in that way. So this is called quadrature encoding. Quadrature encoding means these 2 signals, the clock and the DT. If you are, for example, counting, or if you are rotating this rotary encoder in the clockwise direction, that means clock signal is leading the DT, other signal. So basically, clock is 90 degree. Your clock is leading DT by 90 degree phase, or DT is lagging the clock by 90 degree phase. Okay. So the structure will be something like that. First, this is the counterclockwise direction. When this DT comes first, then comes clock. When it is clockwise direction, the clock comes first, then comes DT.
Yeah.
So in that way, so there are 2 things. So if A becomes actually A, so it is written in the reverse order. A is basically knob turned clockwise, otherwise it is counterclockwise. Now question is that the rotary encoder replaces what? Rotary encoder actually replaces the buttons, switches, and probably and imagine that you have let's say menu driven system that we have talked about, or I had actually thought of some other very interesting projects. For example, okay, let me just one second. Just one second. Ma. Excellent. So, I have thought of making a very interesting kind of digital multimeter. Okay, consisting of an Arduino powered by a smartphone. So I will make it happen with you within 2 months. So what you need to do, we have a sort of rotary encoder right along with you, and we have this multimeter would measure DC voltage, DC current, and DC resistance, capacitance, and some of the stuff, barring the AC parts actually. And entire thing needs to be driven by the smartphone. Smartphone, there has to be an app. I will design the app. Don't need to worry about all such things. But once from the app, actually, you select, let's say, ohm, it will set the system such a way that it will measure the resistance. It will measure up to 10 ohms to 10 ohms. I have designed the ohm meter also. I have the ohm meter coding and hardware with me, so I can share with you any point of time. But that thing I have designed with buttons and switches and resistance, which is a bit troublesome. Because every time you need to press the button, let's say 1, 2, 3, there are 3 buttons. One is, for example, start, second one is reset, third one. So you keep on increasing either number of buttons, or you need to check. For example, button press 1 is for resistance, press 2 for voltage, press 3 for something like that. And we have seen in the actual multimeter, there's a slotted, what should I say, the knob changer, right? Once you place the knob in the ammeter, it will measure the current, stuff like that. Yeah. Similarly, the rotary encoder actually. So we have the, very basics of rotary encoder. Initially, so before moving on, it's better to have a very simple thing to know whether how to measure the rotation in clockwise and how to measure the rotation in counterclockwise. Okay. Okay, now we can take a 2 minutes break, right? After that, we'll be back at the podium. Take it. Okay.
Yeah, net.
Yes, let me unmute. Okay, fine. So we come to the rotary encoder part. So now there are certain reasons so that we can use the rotary encoder for interrupt purpose also. We'll see in the couple of examples. How do you connect the rotary encoder into the normal mode? Okay, the program driven mode as well as the IO mode. I mean the interrupt mode. So first of all, we'll be seeing. I mean, of course, the normal programming mode. So we have, just like you, the hash define. We have few inputs. Okay. Let's assume the first input is CLK clock, which I've connected to the pin number 2, right? And then we have defined DT, the reverse clock 3. Every what should I say? Every why it's called DT, that every rotated. Okay, when this a rotary encoder is rotated or is taken a movement, it's called detent. Okay, detent is means in one bit of rotation, right? That is why it's called a detent actually. Next comes define switch, right? We have a switch. Switch is basically 4. And let's assume we have another define, let's say LED, which is clockwise. That is okay. That is 12, because 12 is red. Next we have defined LED CCW. We have 12, 10, right? 10. Next, we placed a counter variable equals to 0, and int. Let's take another example variable, which I'll be talking later. Counter state, current state clock equals to current state clock, and int last state CLK equals to, okay, that is also, and string current direction equals to, empty, and unsigned long button. Last button press equals to 0. Okay, this is for debouncing. We'll see. We have a counter variable, current state clock, last state clock, current direction, right? So we can set up, declare pin mode, clock as input, right? Okay, clock as input, pin mode, TT also as input. SW switch is basically input pull up. Pin mode. Output. Okay, and we have a serial monitor, right? Are they all set up, set down? Okay, now see, Ravi, there are two variables, right? One is a last check, one is a current state check. Okay.
Yeah.
So just by first we do one thing before getting into the this loop program. We need to save, or let me see. I would like to know what is the state of the clock. I mean, clock input of the rotary encoder. Okay, so this is basically clock. So what is the state of the clock input? So I just need to know what is the last state of the clock input. Fine. So yes. Okay, so let's see. Design. Okay, fine. Last check is basically last check. Fine. So within void loop, again, now we check what is the current state of the rotary encoder. Okay. Digital read clock. Okay. What is the current state of the clock input within the loop? So if there's a condition, if the last and the current state they are different, then the pulse occurred, right? So last and the current state are different. That means you have rotated clock. I mean your encoder either in clockwise and the anti-clockwise direction. So there is a if statement. So if is sorry, this one actually, this one not equals to the last check clock, and the current state is clock basically one means either you have rotated, you have taken one dent actually. So you are within the loop actually. So the counter either in the counter basically, so your rotary encoder is incremental. Now to count whether it's clockwise or anti-clockwise, now to put another if statement to check whether digital read DT, because DT is another input you have specified at pin number 3, right? So digital input T, if not equals to the current state of clock, right? The current state of clock means this one. If these two are not same, that means you are in the counterclockwise directions. Okay, fine. So if these two are not same, that means your clock actually is basically, that you're in the counterclockwise direction. So either is clock is leading your D10 signal by 90 degrees. So digital read DT not equals to current consist clock. So they are in the counterclockwise direction. So that means you need to decrement the counter which is initially 0, and we put current directions, that is a string. We just write CCW or counterclockwise directions. Okay, and now there's a digital, right? We have a particular digital pin that is counterclockwise, that is LED CC0. We just put it on, just turn it on. High. So the condition is that if the current state not equal to last state, fine, and the current state is 1, that means you have incremented the rotary, this rotary encoder by 1. So whether you are in the clockwise or anti-clockwise has to be directed by checking the other input. If two inputs are not same and the dt not equal to current state flow, that means you are in the counterclockwise direction. So I am defining the conditions for the counterclockwise direction. That means it decrements the counter by 1. It puts current direction string to CCW, that is a counterclockwise, and it will turn on the corresponding lead corresponding to the counterclockwise direction. Okay. Okay. Next comes the clockwise direction part. Right. Now encoder is the clockwise direction, so you don't need to check the other condition. Else part is basically by default the clockwise. So we can cross check this part and put it over there. So counter becomes counter plus plus, and it becomes CW, and this is CW, and this is also low, right? We have to put this is also low. So this is also low. So clockwise is low, counterclockwise is high. Now the clockwise is high, the counterclockwise is low. Okay, so that is basically your condition. Otherwise, it will print basically serial dot print ln directions directions string current directions and the rotations, and number of rotations, and the number of rotations string counter. Okay. So I think that concludes our encoder part, but you're not done. You're yet to be done. You have to write the statement for the switch purpose. So this is the one, I think, serial println statement that will get your job done. Right, fine, we're done. So this is the final if statement. Okay, so we're done with the encoder part. Now let me consider this one int. Let's say the B state equals to digital with pin number 4, that is, I think, SW, right? SW. Okay. So now, as it's an input pull-up mode, right, Ravi? Okay. Now one condition is there. The last check. What is the last check? Last check should be equals to the serial println after something. Last place should be equals to current, right? That means next state equal to present state, or present state equal to next state. Yes. Now we are reading the switch statement. So if this state is basically low, so that means if button state is low, that means you have pressed the button. Now to wait at least 50 milliseconds just to avoid the the debound statement. It's a small software. It's not as hard, as much hard as we used in the debounds put. Actually, it's a simple one. If the millis is let's say millis minus last button state is there, right? Last button state. This is basically greater than 50 millisecond actually, then you are rest assured the button has been pressed properly. So serial print button pressed. Okay. And you close this if statement. Last button. I think last button press. Yes, last button press. Last button press equals to millis, right? This if I think. If millis is this one is right. Okay. So finally we have last buttons. We are done. Small delay. That's a one. Okay. Okay. Let me compile and then I'll tell you what we are doing actually. Acha, that's just let me connect the switches. Ravi. Okay, just I think one of the switches, one of the keys been removed. Clock is clock is 2, right? Clock is 2, DT is 3, it is switch. Excellent. Switch is 4, DT is 3. Right. Clock is basically 2, DT is 3, and the switch is 4. 2, 3, 4. Take it. Shit, excellent. Just clock is 2 digits. Clock is basically 3. Right. And switch is 4. Excellent. So I can open the Iridium. You see, okay, I think it's better that we take this one. We clear the output and we put a reset button. Yes. Okay. I think is it high? Is it quite good? You see the LED is actually red LED for counterclockwise and it is for the clockwise. Counterclockwise actually green and clockwise for red. Okay. So just if I turn 1, you see the red LED glows, right? This is the red LED. Okay. And if I press, let's say button pressed, okay, button pressed, and another clock 2, 3. I'm just rotating clockwise, okay, 4, 5, and I'm counterclockwise. See the green LED counts. Counterclockwise. Okay. 3, 2, 1, 2, 3, 4. This is counterclockwise, all -1, and then clockwise is all red. 2, 3, 4, 5, 6, 7. Okay.
Yeah.
When clockwise, it is red. When counterclockwise, it is green. When clockwise, it is red. When counterclockwise, it is red. And you can press button over there. Okay. So this is how we can actually, you know, generalize the normal what should I say, rotary encoder without using interrupt. Actually, there's no interrupt. So what happens is quite simple, straightforward. We have declared two variables, clock, three inputs. We know that one is a clock, that is a straightforward input. One is the DT, which sometimes it is just same with the clock, sometimes it is 90 degree out of phase. When it is 90 degree out of phase, that means this one, right?
Yeah.
This system. So that means when two are same, actually these are clockwise, because this output, it is same. That is, it is written over there. It is quite bad actually. When it is same, this is counterclockwise. It should be right. Yeah. When it is same, the knob actually turn clockwise. That means your clock output is leading your DT. But here the DT output is leading clock when these are not same. So similarly, what we have done, we have actually declared few variables, okay, for the current state clock, last state clock, because clock is actually an input which needs to be monitored properly, because we know the clock state, we can immediately know the DT state. So we need to know what is the last state of the clock and what is the current state of the clock, right? So if the last state of the clock is something and current state is something different from last state, that means the rotation happens. That means that this rotary encoder is being rotated either in clockwise direction or in anti-clockwise direction. Okay? So that needs to be taken care of first. Then comes whether it's counterclockwise or clockwise. So we have two LEDs to cross-check whether it's a clockwise or anti-clockwise. LED CW, LED CCW connected with 10 and 12. One is red, one is green. And three variables for current state clock, last state clock. And we have one string current direction. Sometime for the clockwise, it actually prints clockwise, CW, otherwise CCW, and there is a counter. Int counter. So sometimes it is counting in the reverse order for the clockwise direction, the forward count in the clockwise count. So clockwise direction, it will count forward, otherwise it will count to the reverse directions. So we have declared all the input down. That is very important, Ravi. Within setup, that means the setup runs only once in the program, we know that. So before entering the loop, before entering the actual loop, it must save the last state of the digital, the clock input, whether it's 0 or 1. So that saves the state of the clock. Now, within the loop, we check whether the current state of the clock. Now, if this state, two states are different, and if the current state equals to 1, because we have declared the clock as an input, it can be input pull up also. So as we have declared this current state clock not equals to last button state and current state equals to 1, it means that the rotation happens, right? You have rotated the counter. Now you cross check whether the digital DT not equals to current state of clock or not. This current state of clock is 1, it's fine. If this not equals to this, that means the clockwise, counterclockwise rotation happens. The rotation happens with the counterclockwise direction. So you perform all the conditions corresponding to the counterclockwise direction. Similarly, if the state of DT is as good as the state of clock, that means the current state of clock, that means you are in the clockwise direction. Either one time you decrement the counter, second time you increment the counter. And you put a corresponding string to the variable, and you turn on certain LED and turn off the corresponding LED, and you see this is the actual print button. And now, before moving on to the switch, you always save the current state to the last state. So now the last state becomes the current state. Again, when it actually cross-check for this next time, it will start from this statement also. So now, if the current state is 1, the last state is 1. So when the current state next time becomes 0, then only it takes that rotation into consideration. Next comes the switch. Switch, obviously you can have a normal switch statement also, but just to get rid of this debounce or debouncing, which is a part of this mechanical switch used in Arduino, we just put a small delay using millis command. So last button press is basically you have declared 0. So when this becomes 50, that means when you press the button for at least 50 milliseconds, then this button press has to be ratified as a valid button press. Okay? Then it prints the button pressed, and then it put the millis button. That means 50 is millisecond in the last button press. Now the last button press becomes 50. But the next time it keeps on increasing. When you press the button again for the next time, it again executes the millis button. Now it checks whether this difference is greater than 50 or not. As of now, last button press initially it was 0, but now it becomes 50. So at least this millis should be 100 or maybe 101 to make the difference, which is greater than 50. That means for every button press, a 50 millisecond time would be elapsed to make sure that whether you have pressed the button properly or not. Okay. After that, you just put a delay and it happens over the time. Now, the question is that why you have connected pin number, 2 and 3, clock and DT to the pin number 2, 3. There can be so many inputs. We could have connected these two clock and DT to any of the inputs, right? Okay. All the digital inputs are available. But 2, 3 is basically for the interrupt purpose, although we haven't used the interrupt as of now. As of now, we haven't used the interrupt. But, hello?
Yeah, listening.
Oh, sorry. I think my voice might have muffled actually. Anyway, so in case of interrupt, what we actually did that in case of interrupt, nothing will be there in the void loop sections. Everything has to be written inside a special program which is called ISR. You can put it down. You can take a note. This is called ISSR or ISR, interrupt service subroutine or interrupt service routine, which is also called the interrupt handler actually. So that's a program which is separate from the software, and you don't need to call the program. The previous case, what I've shown you, the last cases, that the blink, blink function needs to be called from the main program, that is from the main void loop, right? Okay.
Yeah.
Blink, because without, let's say that you have written the blink, but you forgot to declare the blink within the void loop. So no way it will be called, and it will not perform your task. So blink, the function needs to be called either from the setup or loop. If you call the function from the setup, it will run only once. If you call it from the loop, it will run indefinitely. But what about the interrupt handler? Interrupt handler need not to be called up from the loop or the setup itself. It will call itself. Okay, it will call itself when a certain condition is being met. Okay, what I'm trying to make you understand that the blink function that you have written in the last program has to be called from either setup functions or loop function, because Arduino there are only two software functions available, software void functions available. One is setup, one is loop. So the functions, all the functions which are there, which are existent in your program, must be called from either of the two functions. Okay.
Yeah.
Okay. But in case of interrupt, what happens? You don't need to necessarily prototype define the prototype of the function and call the function. You just write the function at your own convenient space, at your own convenient, definitely places actually, and the function would be called by itself when a certain condition is being met. Now, what are the conditions? Condition is what? In case of clock and DT, condition is what? Condition when this clock and DT, either of the two inputs, changes their last state, right? If either of the two inputs changes from the last state to another state, then you expect a certain rotation to occur in clockwise or the counterclockwise. Otherwise, it will not perform anything. Okay, that's a task. So instead of writing everything in the loop, what you can do, we can write everything inside an interrupt program. So we don't need to write the entire program. I just copy and paste just to make you understand what is the interrupt, and maybe after that we'll see what are the other stuffs available within the interrupt. So for this one, yes, I just copy all such things because these are necessary. Yeah, another. Acha, I think it's better to copy this program to you.
Just share
The,
that book link also.
book links.
Yeah, just now the Rotary encoder book link is there, right? A small document.
अच्छा रोटरी, हाँ रोटरी एनकोडर, ओके 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 ठीक है. रोटरी एनकोडर एग्जाम्पल, ठीक है, फाइन, that is there. Save it as a Google Drive. Okay, now I move to another one. Just copy over there because it's you. Sorry, full program to now. Yes. Yes. अच्छा, okay, fine. So setup is there. Yes, setup is there. Fine. Okay. Now there are two things to be written over there apart from all such discussions that we have taken, like for example last one also. Yeah, after that, see Arduino pin number 2 and pin number 3 also called interrupt 0 and interrupt 1. Okay, so you can define this is 0 means basically pin number.
I want to ask you.
Yeah, sure.
Here 2 and 3 or analog 2 and 3, right?
2 and 3, no, analog not 2 and 3, because this rotary encoder converts this angular rotation into a digital bit, into a digital, I think, voltage. It's not an analog encoder. And what encoder
Yeah,
you have, what encoder
it's not like a variable.
Of course, no. It will not perform, because if you go through, I'll share the link also. It will just the 2 clock pulses. Once this either of these slotted actually this either of the input comes in contact with the ground pin, it will provide a clock pulse. Nothing more. Actually, after that, inside this rotary encoder, there is an IC which generates a square wave, and the square wave is something. What should I say? It's a monostable. Not every time it will generate the square wave. It will generate the square wave, 2 square waves. One from the clock A, second one is a B, and 2 are in the phase quadrature. If they are actually, they are not same. Phase quadrature means either A is leading B or A is lagging. Okay, so there will be a phase difference, phase shifting circuit in between the encoder, rotary encoder. I think at the back side of the rotary encoder, you see there are 3 resistors, R1, R2, R3, and within this encoder, it will have some capacitive element to provide the necessary phase shift. Okay, RC element. So it will provide a 90-degree out of phase shift. That is why it's called a phase quadrature also encoder. This A and B, they are in the phase quadrature. These two are not equal. See, either of these two, even if these are equal, they are actually in terms of phase, they are leading or lagging. And that is why it is providing, it is this, let's say it is 1, it is 0, or if it is 1, it is 0. So we are actually taking the digital inputs. And that is why we have connected the Arduino digital inputs, not the analog input. Valid question.
Can you share that document link?
Yeah. I'll once the meeting is over, I'll send the document link as well as meeting link. Okay, recording. Okay, this one.
Yeah.
And I think I will add some extra portion to the Untitled document. I'll just finish it, and maybe within a couple of minutes I'll be sending everything. Okay.
Yeah.
Okay. So again, one more thing is the Arduino Interrupt. I think that is there, and that is very much important topic for our discussion in the other sections. See, attach interrupt is a command available for the Arduino. Attach interrupt, I think you better say that is a, what should I say? Is a interrupt handler actually, or you can say is the interrupt process available in the Arduino. Now within the attach interrupt, I think module, you need to specify 3 arguments. One, the pin needs to be used as an interrupt pin, maybe pin number 2, pin number 3. So you can use 0, binary, sorry, integer 0, decimal 0 or 1. Decimal 0 means you are using pin number 2. Okay. If you put 1, it means you are using pin number 3. Or you can say simply this command, that is digital pin to interrupt pin number 2 or 3. So there are 3 arguments within the attach interrupt command, just like this. I think yes, this is the syntax. See, attach interrupt. You write the attach interrupt within bracket. This is a pin. If you use pin number 2, you just write digital pin to interrupt 2. If you use pin number 3, use digital pin to interrupt 3. Or instead of writing the entire big string, you can write simply put a 0. 0 means pin number 2 will be by default used as interrupt. Okay.
Yeah.
And
yeah.
It can be 1 also to configure pin number 3 as an interrupt pin. So there are three type of ones. So attach interrupt this one. So pin comma ISR. ISR means what I've discussed right now, interrupt service routine. That is a function. That means ISR means ISR is basically a function which tells you what things are, what tasks is to be performed when processor is being interrupted. Okay, when the interrupt occurs, what tasks actually needs to be performed. For example, it will take a count, or it will keep a track of how many rotations taken, how many rotations have been taken place from the rotary encoder, whether it's clockwise, counterclockwise. It will take a note and it will turn on the certain LEDs, or it will print something. That is the task to be happened. So this task has to be written inside the ISR. And next, mode. Now mode is a keyword that triggers the particular ISR. I've told you that ISR need not to be called from the void loop. So who will call ISR? Okay, ISR has to be called, right? So when certain condition is met, what are the conditions? Condition is when you change the rotary encoder. That means once you change the position of this shaft, either clockwise or anti-clockwise, then ISR should be called. That is the condition. So the mode has to be change. So mode, there are different parameters of the mode. Either it's low, either it's change, it's rising or falling. Here it should be change, right? That means when it changes the previous state to another state. That means if the previous state is 0, and when you're changing the rotation, the shaft, it will change the position by 0 to 1 or 1 to 0. In that case, that particular ISR needs to be called by itself. So we need to write down. So after last button check, actually, yes. What is the next? Attach interrupt, right? Attach interrupt. So, I think that somehow. Shit. So, yes, attach interrupt. Attach interrupt. So pin number 0. Let's assume that pin number 0. So 0 is basically pin number 2, which is basically clock, and 1 is basically DT. Now, the name of the ISR is, for example, just take a name. Let's say update encoder. Okay, the name of the function is update encoder. You have to write the update encoder. Okay, and next we have a button called change, right? So yes. Okay, fine. So that is the format of this. Again, I put another attach interrupt for 0, for 1, because we have 2 inputs, right? One is a clock, one is a DT. Okay, so one clock is connected with 0, second one DT happens. Both the cases, it will update the same function. Okay, so void loop, what happened? Void loop, I write only this button state, nothing like that. This one. That is there. Because I don't want, because we don't have in more than 2 interrupts, we cannot put a switch as a button as an interrupt. So, but there's a classic example which I will show by tomorrow, maybe the day after tomorrow, where you can put switch as an interrupt, and you can put one of the clock and DT as interrupt. So you can use one of the clocks or the DT signal as an interrupt, as the switch as an interrupt, to make everything happen parallelly. Okay, That is also possible.
Yeah.
So anyway, so switch. Yes, that is the crux of the rest of the thing will be written inside a function called void. What is the name of this one? Is a update encoder. Fine. Now just copy the entire portion of the void loop and paste it over there. We've already written from here also. Yes. Yes. See, the variable, everything has been declared, right? So void encoder basically checks whether the current state, same thing, the current state is the clock state and all, and everything is same. Yeah, the last state is basically clock state. Okay. So the void loop portion consists of only the switch, which is not the interrupt, right? And you have to take into account the switch state also because you have a button to come. So button is basically declared as a normal IO program mode. And the rest of the two inputs, which are the clock and DT, these have been declared as an input, interrupt. Okay. So this is the program. Yeah, I'm compiling. So, yeah. Done uploading. See. Again. Oh, PDN also there. Okay, fine. You see that the button is basically on the loop portions. Button is basically on the loop portion, so it is basically provided the button. But whenever I change, see, clockwise rotation, and still it is counterclockwise also provides. Counterclockwise -3, and this is clockwise, and it's quite quite smooth, right? I'm just moving over there. See, it's quite smooth, right? So you can use, I mean, for any other, I mean, whether the calculation is more precise and accurate. Actually, this is called. This is counterclockwise, right? Counterclockwise, 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 counterclockwise. Fine. And you have a button. So see, the interrupt and IO, two things can occur simultaneously, and the operation is quite straightforward. And you could have mentioned, what is the big deal? What's a big deal actually? Because you have already done everything in the program. But see, the main program actually, see, the main program becomes quite small, right? Quite simple. So if you have a more sensor to come, right? If you have more sensor to be attached or to be hooked up with a microcontroller, so you could have done the same thing within the loop, which cannot be a part of the, let's say, the interrupt. And you have to choose. You have to choose. Rigorously and meticulously that which device needs to be given the highest priority. The highest priority device will be connected to the interrupt. That means that device needs to be serviced first. Okay, apart from barring the other devices. So let's say you have a 5 sensors and let's say 4 actuators. Out of that, 2 are very crucial. And if you miss out one data from, let's say, GPS sensors or clock, RTC, or maybe some other stuff, you might lose a lot of other stuff as well. So you better connect these two as the interrupt. And we have another stuff to before we call it a day today. See, this is all about Arduino Uno. But if you put the Arduino Mega, see, there are a lot of other interrupts. For example, Arduino Mega, you see, there are 6 interrupts. Okay, 4 to 6 interrupts available for the other Arduino boards. For ESP32, all pins are interrupt. All pins are interrupt mostly. Modern day processors for STM32 and PIC, 90% of the pin you can use as the interrupt. that means they have a parallel threading always running on the face. So here also the beauty of the program, this method, that means this update encoder function, you don't call it, you haven't called it from the loop. The function calls actually, when it calls it actually itself, it will call itself when the certain condition is met. That is when you change the rotation. That's it. So you can put any of our precise device which needs to be service pass, which needs to attention to the interrupt pin. Okay. I mean, for example, some device might not come into the change category. Some device needs, for example, a low to high change. Then you can put a rising, RISI is rising. That means when the device connected to the pin number 2 or 3, that makes a transition, logic 0 to 1, that is a rising. Or if you can state falling, that means when it makes a transition from 1 to 0, then only that particular ISR written inside the attached interrupt, that will be called. Okay, so there can be so many states: logic high, logic low, rising, that means logic low to logic high, falling, logic high to logic low, or simply change. That means, but when it actually states its change from 0 to 1 or 1 to 0, whatever, the function will be called. That's the simplest thing that we have. We have seen today, but it can be a crucial one. Obviously, we'll be seeing in case of a critical example of rotary encoder that I will preferably connect this button to the pin number, let's say 3, and we have connected in the falling because we have connected the button in the input pull-up. Input pull-up means what? Once you press the button state becomes low, right? Okay. Yeah. So when the button state becomes low, then only the function will be called. Otherwise, no, nothing will be called. So that is one piece of the interrupt actually. Okay. Yeah. So I think, I might copy this program to you. Yes. Okay. Ravi, do you have a class on Wednesday? I'm sorry, Mani. I mean, do you have an office on Wednesday, or Wednesday can we start at morning?
Today is Monday, right? Tuesday, Wednesday. Yeah, Wednesday.
You can let me know.
Yeah.
You can let me know, so if possible.
Yeah, that's what. See, Wednesday, if morning is not possible, evening we can have it.
Okay. Actually, you know, I'm getting totally messed up with all classes packed up at evening, because definitely you guys have come from office and my office work also the morning. But I do have a I don't have a problem if I take classes in the early morning, which I take for you actually, or maybe the late evening. But in between that, what happens, most of the I have certain students from VIT, 10 students VIT, they are actually, you know, when I'm teaching them, you know, the same computer organization architectures. So basically they come after the classes, 6:30, 7:30. That is why today I'm extremely sorry that I got delayed by half an hour for you.
No, actually what happened, I came at afternoon only.
But I didn't know. Otherwise, had I known it before, then I could have taken your class actually.
I texted so I thought you, that maybe I think you have not seen it.
No. Actually, my phone got actually stuck, and I had seen your text, but somehow I didn't reply to you because of I got stuck in work actually. I want to obviously we'll come.
Okay, no problem. We'll do one thing. I'll let you know in tomorrow.
Okay.
Or else we can have class